Welcome to Science Documentary for Sleep Channel. Tonight, we're going to explore something that seems impossible, a place where space folds inward, where time loses its familiar rhythm, where even light cannot retrace its path. At first, it sounds like the beginning of science fiction, yet every observatory on Earth now agrees. Black holes exist. They are not ideas anymore. They are destinations for light. They are scars left behind by ancient stars. And perhaps they are also doors. Not doors built from wood or stone, not doors anyone could ever touch, but passages written into the geometry of reality itself. By the end of tonight, you will understand why generations of physicists have spent their lives asking a single quiet question. What if a black hole does not simply destroy everything? What if it hides something instead? Perhaps another beginning, perhaps another universe, or perhaps something even stranger. For now, there is no need to rush. Allow your breathing to settle. Allow the room around you to soften. Outside your window, night continues its patient work. Trees sway without asking permission. Clouds drift without knowing where they will end. Somewhere, a distant aircraft crosses the darkness. Its tiny lights seem almost motionless, although it travels hundreds of miles each hour. Perspective changes everything. That simple truth will guide us tonight. Because black holes are not only difficult to imagine, they challenge the very instincts that have helped humans survive for hundreds of thousands of years. Our senses evolved for forests, for rivers, for mountains, for falling rain, not for collapsed stars, not for curved space-time, not for gravity powerful enough to reshape time itself. Imagine something very ordinary. You are standing in your kitchen. A single coin slips from your fingers. It falls. It strikes the floor. You hear the sound. You bend down. You pick it up. Nothing feels mysterious. Gravity seems completely familiar. It pulls everything downward. Every day, every hour, every second. Children learn this before they understand numbers. The moon circles Earth because of gravity. Earth circles the sun because of gravity. Galaxies slowly dance because of gravity. Gravity appears simple, almost comforting. Yet this comfort comes from living inside a remarkably gentle corner of reality. Earth is massive. Its gravity shapes oceans, raises tides, holds an atmosphere, keeps every living creature close to its surface. But compared with the great engines of the cosmos, Earth barely whispers. Imagine compressing our entire planet, every mountain, every ocean, every city, every memory of human civilization, into something no larger than a marble. Gravity nearby would become astonishing. Now imagine compressing the sun instead. More than 300,000 Earths, crushed inward, not until it becomes a marble, but until it measures only a few miles across. The result would no longer resemble a star. Its familiar light would disappear. Its surface would vanish. Its future would become something entirely different. A black hole. This transformation feels almost impossible. How can something become smaller, yet more powerful? The answer hides inside density. Picture a pillow. It feels soft, light, easy to squeeze. Now imagine removing every empty space inside its fibers. Every tiny pocket of air disappears. The pillow becomes smaller, heavier, harder. Gravity behaves similarly. Matter itself does not need to increase. Only its concentration changes. As more matter gathers inside less space, gravity becomes stronger. Not because something magical appears, but because space-time bends more sharply. Albert Einstein described gravity differently from Isaac Newton. Newton imagined an invisible force pulling objects together. Einstein imagined something quieter, something almost elegant. Space itself changes shape. Time changes shape. Matter simply follows those curves. Imagine placing a heavy bowling ball upon a stretched blanket. The fabric sinks. Roll a smaller ball nearby. It naturally moves toward the deeper curve. Nothing pulls it with invisible hands. The surface itself guides its motion. This image is imperfect. Real space-time has 4 dimensions, not 2. Yet the metaphor remains useful. The sun curves space-time. Earth follows that curve. The moon follows Earth's curve. Every orbit becomes a conversation between motion and geometry. Black holes represent the deepest conversations ever discovered. The fabric no longer bends gently. It folds downward beyond ordinary imagination. Eventually, The curve becomes so steep, nothing climbs back out. Not light, not particles, not information. At least, that is what classical physics first suggested. But the deeper scientists looked, the stranger the picture became. Because nature rarely enjoys simple endings. Every answer quietly opens another question. If nothing escapes, where does everything go? Does matter simply disappear? Can information truly vanish forever? Or does reality preserve every detail somewhere beyond our reach? For decades, these questions remained almost philosophical. Then technology improved. Radio telescopes spread across continents. Computers synchronized impossible amounts of information. Astronomers combined signals gathered from thousands of miles apart. Eventually, humanity accomplished something extraordinary, not by traveling to a black hole, but by allowing Earth itself to become one enormous telescope. In 2019, the first image of a black hole reached the public. Not a photograph in the ordinary sense, more like a portrait assembled from whispers. Tiny fragments of radio light, collected across the planet, carefully combined, patiently reconstructed. The result became instantly recognizable. A glowing ring, a dark center, silence surrounded by fire. Many people expected disappointment. Instead, the image produced something deeper, wonder, not because it answered every question, but because it confirmed that mathematics written generations earlier had described something real. The darkness in that image was not empty. It marked the region where light could no longer return. A boundary, not necessarily an ending. Imagine standing beside the ocean at night. Far offshore, fog slowly swallows every distant ship. One disappears, then another. Eventually, the horizon itself becomes uncertain. Did the ships vanish? Or did your vision simply reach its limit? Black holes invite the same question. Perhaps what disappears has not ended. Perhaps only our ability to witness it has. Science demands caution, evidence before certainty, observation before belief. No telescope has ever seen inside a black hole. No spacecraft has returned. No message has crossed back. Yet mathematics continues pointing inward, patiently, quietly, as though inviting us to keep asking. Every generation inherits mysteries from the one before. Ancient sailors wondered what waited beyond the horizon. Later generations crossed oceans. Astronomers wondered whether planets circled distant stars. Now thousands are known. Questions once considered impossible gradually became ordinary. Perhaps black holes belong to the same story. Not because every speculation will prove true. Many certainly will not. But because curiosity has always traveled farther than certainty. As tonight unfolds, we will continue moving inward, one careful step at a time. We will discover why light stops, why time stretches, why information refuses to surrender quietly, and why some physicists now wonder whether every black hole could be protecting a secret far greater than itself. For if gravity can fold space deeply enough, perhaps it can also unfold something entirely new. The falling coin has reached the floor, but our journey has only just begun. The next time you walk through a thick morning fog, notice how gently the world disappears. A nearby tree remains clear. A distant house becomes soft. The horizon slowly dissolves into pale gray. Nothing has vanished. Your eyes have simply reached their limit. This ordinary experience offers one of the closest emotional anchors for understanding the edge of a black hole. Not because fog traps light forever. It does not. But because both remind us that seeing depends as much upon the journey of light as upon the object itself. Every morning on Earth begins with returning light. Photons leave the sun. They cross nearly 93 million miles. About 8 minutes later, they arrive here. They bounce from leaves, windows, rivers, mountains, and faces before entering your eyes. Vision is not touching objects. Vision is receiving ancient travelers. Every image you have ever seen is made from tiny messengers that survived an incredible journey across space. Now imagine a place where those messengers can no longer escape. This boundary has a beautiful name: the event horizon. It is often imagined as a surface, yet it is not a wall. It has no texture, no color, no hidden gate. If you somehow floated beside it, you would find nothing solid waiting there. Space would appear almost ordinary. The stars would still shine behind you. Darkness would remain ahead. The event horizon exists because of geometry. It marks the exact distance where every possible future path points inward. Picture yourself walking up a gentle hill. At first, every step forward can easily be reversed. You stop, turn around, walk back home. Now imagine the hill becoming steeper until it transforms into a waterfall. There comes a point where the current becomes stronger than your best swimming. Beyond that point, effort no longer matters. Every movement still feels real. Every stroke still happens. Yet every stroke carries you farther downstream. Physicists often compare a black hole to such a river. Not because water exists there, but because space itself behaves as though it is flowing. Far away. This flow is gentle. Planets orbit comfortably. Light travels normally. Closer inward. The current strengthens. Near the event horizon, space falls inward at the speed of light. Beyond it, space falls even faster. This statement sounds impossible until we remember an important detail. Einstein's theory limits how objects move through space. It does not forbid space itself from expanding, stretching, or flowing. The universe already demonstrates this on its largest scales. Distant galaxies appear to recede faster than light because space between galaxies expands. Nothing breaks Einstein's equations. The fabric changes. The travelers obey local rules. Black holes create a similar surprise, but in the opposite direction. Instead of expansion, carrying galaxies apart, collapsing space-time carries everything inward. This idea changes the meaning of escape. Imagine standing on an airport moving walkway. If the walkway moves slowly, walking backward returns you to where you began. Increase its speed. Eventually, you must run simply to remain still. Increase it again. There comes a moment when even your fastest sprint cannot overcome the motion beneath your feet. Beyond that point, every effort still moves your legs, yet the floor carries you away. The event horizon resembles that invisible line. Light always travels at light speed. Nothing outruns it. Yet, inside the horizon, even light cannot climb against the inward flow of space-time. Not because light has weakened, because every possible direction has changed. This realization often produces a quiet feeling of cosmic unease. We spend our lives believing there is always another direction. Turn left, turn right, climb higher, step backward. Choice seems endless. A black hole introduces a region where every road leads the same way, not through force, through geometry. Curiously, someone falling toward the event horizon would notice nothing dramatic at the exact crossing, provided the black hole were enormous. No invisible alarm would sound. No bright line would appear beneath their feet. Their heartbeat would continue. Their thoughts would remain their own. The boundary exists mathematically, not visually. Yet an observer watching safely from far away would witness something completely different. Imagine waving goodbye to a friend walking toward a distant horizon. At first, they appear normal. Then their movements slow. Their voice fades. Their colors become redder. Eventually, they seem almost frozen, lingering forever near the edge. From your perspective, they never quite disappear. Both experiences are correct. This is one of Einstein's greatest gifts to human thought. Reality depends upon the observer's path through space-time. Time is not a universal drumbeating equally for everyone. It stretches, compresses, bends alongside gravity. Light escaping a black hole also loses energy. As photons climb outward, gravity robs them of frequency. Blue becomes white. White becomes red. Red slips toward invisible infrared. Continue farther. Eventually, the light becomes radio waves too faint to detect. The message still exists. It simply arrives quieter and quieter until the universe itself drowns it beneath older echoes. This gradual fading feels strangely familiar. Human memory behaves in much the same way. Childhood conversations remain somewhere inside us, yet their colors soften, their edges blur. Certain faces become difficult to recall, not because they cease to exist, but because time gently stretches the distance between experience and remembrance. Black holes invite us to think similarly about light. Every escaping photon carries history. Every fading signal tells us something about the journey it survived. Astronomers often read these faint whispers rather than brilliant flashes. The quietest messages frequently reveal the deepest truths. Around many black holes, matter forms a glowing disk before crossing the horizon. Gas circles at astonishing speeds. Friction heats it to millions of degrees. X-rays pour outward. From great distances, these invisible monsters become some of the brightest objects in the universe. It is another beautiful paradox. The darkest places are often surrounded by extraordinary light. Without that glowing material, many black holes would remain invisible forever. We discover them not because we see darkness directly, but because we watch neighboring stars behave strangely. Their orbits bend, their light shifts. Invisible gravity leaves visible fingerprints. Science often works this way. We rarely observe fundamental reality directly. Instead, we notice consequences. Wind cannot be seen, yet trees reveal it. Gravity remains invisible, yet planets trace its shape. Black holes hide themselves, yet entire galaxies quietly rearrange around their presence. Still, every explanation creates another question. If the event horizon is only a boundary, what happens after crossing it? Does falling continue forever? Is there truly a center? Does time itself survive? Or does something far stranger await beyond every equation we currently understand? The fungi has now disappeared behind us. Ahead waits a place where even time begins changing its pace. The horizon was never the destination. It was only the threshold. There is an old comfort in listening to a clock late at night. Each second arrives with quiet confidence. Tick, then another, tick. The rhythm feels permanent, reliable, almost immune to change. Whether you are awake or asleep, whether rain falls outside or snow gathers silently upon rooftops, the clock continues. It becomes so familiar that we begin believing time itself behaves exactly like its steady sound. Yet the universe has never made such a promise. Time is not a river flowing equally for everyone. It is more like a landscape, sometimes flat, sometimes gently rolling, sometimes descending into valleys so deep that every traveler experiences the journey differently. This idea feels strange because nothing in ordinary life prepares us for it. Two friends sharing the same room grow older together. Their watches remain synchronized. Their conversations unfold in the same rhythm. Every sunrise appears to belong equally to both of them. Earth's gravity is simply too gentle for us to notice otherwise. But gravity does affect time. It always has. The difference is unimaginably small here. Imagine climbing a tall mountain. Your watch at the summit actually runs ever so slightly faster than an identical watch resting at sea level. The effect measures only tiny fractions of a second. You would never notice without extraordinarily precise instruments. Yet modern atomic clocks measure it routinely. Even satellites orbiting Earth experience time differently from clocks on the ground. Engineers must constantly correct these differences. Otherwise, GPS navigation would drift by miles within a single day. The phone resting quietly beside your bed works because Einstein was right. This realization often surprises people. Relativity feels distant, abstract, reserved for physicists surrounded by chalkboards. Yet every journey mapped across highways, every airplane tracked above the clouds, every package delivered through satellite navigation quietly depends upon time, refusing to remain perfectly universal. Now imagine replacing Earth's modest gravity with something millions of times stronger. Imagine approaching a black hole. The gentle difference between mountaintop and valley becomes enormous. Picture two identical hourglasses. One remains safely aboard a distant spacecraft. The other slowly descends toward the event horizon. Both begin together. Sand falls smoothly through each narrow neck. At first, nothing appears unusual. Gradually, the descending hourglass begins falling more slowly. Not because its sand has changed, because time itself flows differently there. This is gravitational time dilation. The phrase sounds technical. The experience would feel almost poetic to the traveler descending. Nothing seems wrong. Their heartbeat remains steady. Their breathing keeps its natural rhythm. Thoughts arrive one after another exactly as expected. They eat, sleep, blink, remember. Hope. Everything feels ordinary because every process inside their body slows together. But to someone watching from far away, an astonishing transformation unfolds. The traveler appears to move more slowly. Each wave lasts longer. Each heartbeat stretches farther apart. Their voice grows deeper as light loses energy, escaping gravity. Eventually, every movement seems suspended, almost like a leaf caught forever in still water. From the distant observer's perspective, the traveler never quite reaches the event horizon. Time itself becomes an endless farewell. Meanwhile, the traveler experiences something entirely different. They cross the horizon, continue inward, leave the waiting observer behind. Both stories remain correct. Neither observer is mistaken. Reality simply allows different paths through space-time to produce different experiences of time. Few scientific discoveries have challenged human intuition more profoundly. For centuries, philosophers argued whether time existed independently of everything else. Newton imagined an invisible cosmic clock ticking identically throughout creation. Einstein gently dismantled that certainty. Time became woven together with space, matter, and gravity. Remove one thread, and the entire tapestry changes shape. Imagine reading a long novel. A reader beginning, Chapter 1 occupies a different moment than someone reading Chapter 15. Both hold the same book. Neither version is false. They simply occupy different places within the story. Space-time behaves similarly. Every observer follows a unique path. Every path carries its own rhythm. Black holes reveal this truth more dramatically than anywhere else we currently know. Astronomers have even imagined extraordinary journeys based upon this effect. Suppose an explorer spent only a few hours orbiting extremely close to a supermassive black hole without crossing the horizon. After returning home, they might discover decades had passed elsewhere. Friends would have aged. Children would have grown old. Entire civilizations might have changed while only an afternoon passed aboard their ship. This possibility is not fantasy invented for cinema. The mathematics permits it. Reality simply demands conditions almost impossible to survive. Even so, the equations remain beautiful. Time stretches, yet never breaks. The closer gravity pulls, the slower clocks appear to run from distant viewpoints. This slowing creates another remarkable consequence. Black holes become natural archives of the ancient universe. When astronomers observe distant galaxies, they already look backward through time because light itself requires years, centuries, or billions of years to arrive. Looking deeper into space means looking farther into history. Gravity around black holes extends this strange relationship even further. It reminds us that time is not merely something we measure. It is something the universe continuously shapes. There is something deeply comforting hidden within this idea. Human life often feels rushed. Days disappear into calendars. Years quietly become memories. We worry about time slipping away because our experience remains anchored to one steady rhythm. The cosmos offers another perspective. Somewhere, clocks race ahead. Elsewhere, they drift almost motionless. The universe possesses no single heartbeat, only countless local rhythms woven together into one vast composition. Perhaps this explains why ancient cultures often imagined eternity not as endless duration, but as a place beyond ordinary time altogether. Standing beneath the stars, They sensed something difficult to express. They lacked Einstein's equations. They possessed only wonder. Sometimes wonder reaches truth before mathematics does. Yet another mystery waits. If gravity can slow time almost to stillness, what happens deeper inside the black hole? Does time continue forever? Does it reverse? Does it end? Or does the very meaning of past and future dissolve into something language can scarcely describe? To answer those questions, we must first understand an even stranger idea. Inside a black hole, gravity is no longer merely pulling objects inward. Space itself begins to move. And once space begins flowing faster than light, every familiar map of escape quietly fades behind us. Stand beside a quiet river for a few minutes. At first, the water seems almost motionless. Small ripples drift across the surface. Leaves float past without urgency. Sunlight breaks into tiny reflections that shimmer and disappear. It feels peaceful because your mind immediately understands the scene. If you wished, you could step into the shallow edge. You could walk upstream. You could return to the bank whenever you pleased. A river always seems to offer choices. Now imagine that same river becoming wider. The current grows stronger. The water deepens. You begin swimming instead of walking. Your progress slows, but you still move where you choose. Every stroke matters. Every decision changes your path. Then imagine something even stranger. Ahead lies a waterfall so immense that no swimmer has ever escaped it. Long before reaching the edge, the current becomes overwhelming. You continue swimming with all your strength. Your muscles still work. Your heart still beats. Yet every effort only delays the inevitable. The river itself has become the true traveler. You merely accompany it. This image is one of the most useful ways physicists explain a black hole. Not because black holes contain water, but because the flow belongs not to a river, it belongs to space itself. That sentence deserves to be read slowly. Space itself can move. For centuries, people imagined space as an empty stage upon which stars and planets performed their motions. The stage never changed. Only the actors did. Einstein quietly replaced that picture. Space became dynamic, flexible, capable of stretching, bending, rippling, and collapsing. Once that idea is accepted, many mysteries begin to soften. Galaxies drift apart because space expands. Gravitational waves travel because space ripples. Black holes trap light because space flows inward. Imagine standing on one of those moving walkways inside a large airport. When the walkway is switched off, walking feels ordinary. Turn it on, and the floor quietly helps you move. Walk against it, and progress becomes slower. Increase the speed enough, and even running begins to feel difficult. Now imagine a walkway with no maximum speed. Faster, still faster. Eventually the floor moves as quickly as light itself. At that precise point, even a beam of light trying to travel backward merely remains in place. Increase the speed further. Now every photon, every spacecraft, every atom, every possible traveler continues moving at its own maximum speed through local space. Yet, the space beneath them carries everything inexorably forward. Nothing has exceeded the speed of light. Nothing has broken Einstein's laws. The geometry itself has changed. This is one reason black holes remain so difficult to visualize. Our instincts always assume space stays still while objects move through it. Near a black hole, that assumption quietly fails, far from the event horizon. The inward flow is gentle. Planets orbit comfortably. Comets swing past and continue on their long journeys. Light bends slightly as it passes, producing beautiful gravitational lensing. Entire galaxies sometimes become distorted into glowing arcs because invisible masses curve the light behind them. Astronomers use these cosmic distortions almost like magnifying glasses, revealing objects that would otherwise remain hidden. As one approaches the black hole, the current strengthens. The bending becomes more dramatic. Paths that once appeared straight begin curving inward. Photons leaving nearby stars no longer travel exactly where intuition expects. They spiral, they arc, they circle. Some complete entire loops before escaping. Others never escape at all. There exists a remarkable region outside certain black holes where light can orbit temporarily. Physicists call it the photon sphere. Here, gravity bends light into circles. Imagine a whisper chasing itself endlessly around a cathedral until the echo slowly fades. The photon sphere resembles that silent echo. Light becomes trapped in graceful loops before the slightest disturbance sends it either outward toward freedom or inward toward darkness. This region reminds us that nature often prefers delicate balances rather than sharp divisions. Everything near a black hole seems to exist on thresholds. One tiny change decides entirely different futures. A slight difference in direction determines whether a photon crosses millions of light years or vanishes forever. Human lives often feel surprisingly similar. One conversation changes a career. One meeting becomes a lifelong friendship. One decision quietly redirects decades. The universe seems comfortable building extraordinary consequences from remarkably small beginnings. As space continues flowing inward, another phenomenon begins to emerge: tidal forces. You already understand tides, although perhaps not in this form. The moon pulls slightly harder on the side of Earth facing it than on the opposite side. Oceans respond by rising and falling. The same principle operates near black holes, but with breathtaking intensity. Imagine stretching a piece of soft bread. One end remains in your hand, the other is gently pulled away. The loaf becomes longer and thinner. Gravity near a small black hole behaves similarly. Your feet would experience a stronger pull than your head. The difference grows rapidly. Eventually, the stretching becomes extreme. Physicists have given this dramatic process an unexpectedly playful nickname: spaghettification. Despite the humorous word, the underlying physics is profound. Gravity is not merely stronger near a black hole. It changes dramatically across very short distances. Curiously, enormous supermassive black holes behave more gently at their horizons. Their immense size spreads tidal forces over much larger distances. An astronaut crossing the event horizon of such a giant might notice nothing unusual at first. The fatal stretching would occur much deeper inside. Scale changes everything, a lesson repeated throughout astronomy. A tiny neutron star packs unimaginable density into a city-sized sphere. A supermassive black hole can outweigh billions of suns while possessing a horizon larger than our entire solar system. The numbers become so vast that ordinary intuition quietly steps aside. Yet the underlying principles remain beautifully simple. Space curves, time stretches, gravity shapes both. Everything else follows. Still, one unsettling question refuses to disappear. If space itself carries every traveler inward, where does that inward journey finally end? Does every path converge upon a single point? Does space continue forever inside? Or does the universe conceal an entirely different structure beyond the reach of today's mathematics? To approach those questions, we must leave rivers behind. Our next guide will be something far more familiar: a shelf filled with old books. Because some physicists now suspect that every story, every atom, and every memory swallowed by a black hole may never truly vanish. They may simply be written somewhere we have not yet learned to read. Walk into an old library just before closing time. The room feels different from almost every other place on Earth. Dust hangs quietly inside narrow beams of afternoon light. Wooden shelves carry books written by hands that disappeared generations ago. Some pages have yellowed. Others still smell faintly of ink. Every volume contains voices that continue speaking long after their authors have fallen silent. A library performs a remarkable act. It preserves information. Paper grows fragile, leather cracks, bindings loosen, yet the stories survive because the information remains carefully arranged upon each page. Maing's simple experience offers another gentle anchor for one of the deepest mysteries surrounding black holes. Can information ever truly disappear? At first, The question sounds strangely philosophical. We lose photographs. We forget conversations. Letters burn in fireplaces. Hard drives fail. Entire civilizations vanish beneath deserts. Human experience seems filled with forgotten things. Physics tells a different story. According to the deepest principles of modern science, information should never simply cease to exist. The arrangement may change, the form may transform, order may become astonishingly difficult to reconstruct, but the fundamental information describing reality should always remain somewhere within the universe. Imagine dropping a sheet of paper into a campfire. Within minutes, the page is gone. Only drifting smoke and gray ash remain. To ordinary observation, the words have vanished forever, yet every atom still exists. Every carbon molecule, every drifting particle of smoke, every tiny pulse of heat escaping into the evening air. If someone possessed impossible precision, they could, at least in principle, trace every particle backward and reconstruct the original page. Reality has changed shape. It has not forgotten. Black holes challenge this comforting belief. Suppose you throw that same book toward the event horizon. It falls. It crosses the boundary. Then nothing returns. No pages, no ashes, no smoke, no scattered atoms, no readable message. From the outside, every chapter appears erased. If black holes truly destroy information, then one of the most successful foundations of physics quietly collapses. This puzzle became known as the information paradox. Its name sounds technical. Its implications reach astonishing depths. Imagine spending decades assembling the greatest library ever created. Every scientific discovery, every poem, every piece of music, every photograph, every human memory carefully preserved upon endless shelves. Now imagine one silent doorway at the far end of the building. Every book carried through that doorway disappears forever, leaving no trace behind. Would knowledge still possess permanence, or would reality itself become unpredictable? Nature seems deeply uncomfortable with true forgetting. Again and again, physical laws preserve hidden details even when appearances suggest complete loss. A broken vase scatters into countless fragments. A cloud dissolves into invisible moisture. A melody fades after its final note. Yet the atoms remain. The energy remains. The information describing those atoms should also remain somewhere. The question is where? During the 1970s, physicists began looking more carefully at the event horizon itself. Instead of imagining it as an empty boundary, they wondered whether it might possess subtle physical properties. Could the surface somehow record everything crossing it? Imagine walking across fresh snow. When you leave, your footprints remain behind. Hours later, another traveler can read your path without ever meeting you. The snow stores information. Not perfectly. Wind eventually softens the edges. Sunlight melts the surface. Yet for a while, your journey becomes part of the landscape itself. Some researchers began imagining the event horizon in a similar way, not as a wall, but as a cosmic record keeper. Every particle crossing the horizon might leave an unimaginably tiny imprint upon its surface. The object disappears from view. Its information does not. This idea slowly evolved into one of theoretical physics' most beautiful concepts. The area of a black hole's event horizon appears connected to the amount of information it can contain. Notice something unusual, not its volume, its surface. Libraries store books inside buildings. Black holes may store information upon their boundaries. This quiet shift would eventually inspire an entirely new way of thinking about reality itself. But that revelation belongs a little farther ahead. For now, another surprising discovery enters the story. Black holes possess entropy. Entropy often receives an unfair reputation as the measure of disorder. A more gentle description may be the number of possible microscopic arrangements hidden beneath an ordinary appearance. Imagine two decks of playing cards. One remains perfectly ordered. The other has been shuffled thousands of times. Both contain the same 52 cards. The difference lies in arrangement. Entropy counts possibilities. Black holes possess astonishing amounts of it. That fact suggests they hide unimaginably rich internal structure, even if we cannot directly observe it. Jacob Bekenstein was among the first physicists willing to take this idea seriously. He proposed that black holes should have entropy proportional to the area of their horizons. At first, many experts doubted him. The proposal sounded almost impossible. How could an object that seemed completely black contain thermodynamic properties? How could silence possess temperature? How could darkness carry information? Science often advances through such uncomfortable questions. Not because every bold idea survives, most do not, but because nature occasionally rewards those willing to ask what everyone else quietly avoids. Years later, Stephen Hawking explored these ideas further. His calculations would transform black holes forever. They were not perfectly black. They were not perfectly silent, and they were not eternal. That conclusion startled the scientific world because it created an entirely new challenge. If black holes slowly disappear over unimaginable spans of time, what happens to the information they have stored? Does it escape gradually? Does it remain encoded somehow within the faint radiation leaving the horizon? Or does the paradox become even deeper than anyone first imagined? Notice how each answer opens another doorway. The library preserved its books. The snow preserved its footprints. The horizon may preserve something even greater. Perhaps every atom, every photon, every moment, every history, nothing truly forgotten, only rewritten into a language we have not yet learned to read. If that possibility is correct, then black holes are not merely cosmic graves. They may be the greatest archives the universe has ever created. Yet archives are meaningful only if something eventually reads them. Our next step brings us to a remarkable discovery, one that begins beside the warmth of a fading fire and ends with black holes quietly glowing in the deepest darkness. On a cold evening, there is something quietly reassuring about sitting beside a fireplace. Flames rise and fall without hurry. Small pieces of wood collapse into glowing embers. Heat spreads gently across the room. Even after the fire begins to fade, warmth continues lingering in the stones around it. Nothing burns forever. Every flame slowly gives away its energy until only faint orange light remains. This simple scene teaches one of nature's oldest lessons. Anything that possesses warmth eventually cools. Anything that contains energy slowly shares it with the world around it. For centuries, black holes seemed to be the single exception. They absorbed everything. They returned to nothing. Light entered, matter entered, heat entered, silence remained. Physicists describe them as perfect cosmic prisons. Whatever crossed the event horizon became permanently hidden from the rest of the universe. The story appeared complete. Then Stephen Hawking asked an unusually simple question. What happens when quantum physics enters the picture? Until that moment, black holes belonged mostly to Einstein's theory of gravity. Quantum mechanics described an entirely different world. The restless behavior of particles, tiny fluctuations, invisible probabilities constantly dancing beneath ordinary reality. Each theory worked extraordinarily well, yet together they often refused to cooperate. Black holes became one of the rare places where both had to matter at the same time. Imagine looking at a calm lake just before sunrise. From a distance, the surface appears perfectly still. Walk closer and the illusion fades. Tiny ripples shimmer everywhere. Small insects touch the water. Gentle currents move beneath reflections. What seemed perfectly smooth was quietly alive with motion. Empty space behaves in much the same way to everyday experience. A vacuum appears completely empty. Quantum physics tells another story. Even the emptiest region imaginable refuses to remain perfectly still. Tiny fluctuations constantly appear and disappear. Pairs of particles briefly emerge from the quantum vacuum before immediately destroying one another. The process happens so quickly that the universe scarcely notices. Normally, these fleeting pairs leave no permanent trace. They borrow energy for an unimaginably brief instant, then return it. The cosmic balance remains undisturbed. Now imagine this restless quantum activity occurring beside the event horizon. One particle appears just outside. its partner appears just inside. Instead of immediately reuniting, gravity separates them. One falls inward, the other escapes into space. To a distant observer, it appears as though the black hole has emitted a particle. No explosion occurs, no dramatic burst of light, only an extraordinarily faint whisper of radiation. This prediction became known as Hawking radiation. Its consequences were astonishing. Black holes were not completely black. They possessed an incredibly tiny temperature. Anything with temperature can radiate energy. Anything radiating energy gradually loses mass. Anything losing mass long enough eventually disappears. The greatest prisons in the universe were slowly evaporating. The process unfolds almost beyond imagination. A black hole weighing as much as our sun would require roughly 10 to the 67th power years to vanish completely. That number is so enormous that writing every zero would fill pages. Compared with it, the current age of the universe becomes almost insignificant. Stars live for millions or billions of years. Galaxies evolve across trillions. Black holes endure for spans so vast that ordinary language quietly surrenders. Yet even they are not eternal. There is something unexpectedly comforting about this. Human beings often search for permanence. Ancient monuments crumble, mountains slowly erode, oceans reshape coastlines, stars exhaust their fuel. Even black holes eventually fade. The universe seems less interested in preserving objects than in preserving transformation. Nothing simply remains. Everything becomes something else. Imagine watching a single block of ice resting beneath warm sunlight. Minute by minute, it grows smaller. Tiny droplets slide across its surface. Eventually, the ice disappears. Yet nothing has been lost. Water remains. Heat has moved. Form has changed. Black holes undergo a similar transformation, although across timescales so immense that even civilizations lasting millions of years would witness almost no difference. The radiation itself would be extraordinarily cold. For black holes created by collapsing stars, the surrounding universe is actually warmer than the black hole. Instead of shrinking today, such black holes absorb far more energy than they emit. Only after the cosmos grows unimaginably older will evaporation truly dominate. That future belongs to an era beyond stars, beyond galaxies, beyond almost everything familiar. Cosmologists sometimes call it the black hole era. Imagine a universe where every brilliant star has already died. No new sunlight rises. No spiral galaxies glitter across darkness. Only isolated black holes remain, scattered through immense distances, quietly releasing the last faint traces of their stored energy. The scene feels almost impossible to picture. Silence deeper than any earthly night. Darkness interrupted only by whispers too faint for human eyes. Time measured not in centuries, but in numbers beyond ordinary comprehension. Yet even there, change continues, patiently, without urgency, without witnesses. Each black hole grows slightly smaller. Each horizon contracts. Each ancient giant slowly approaches its final moment. And here the paradox returns with even greater force. Suppose a black hole eventually evaporates completely. Where did everything it swallowed go? If only featureless thermal radiation escapes. Then the detailed information describing every fallen star, every planet, every photon, and every atom seems permanently erased. Quantum mechanics strongly resists that conclusion. Its equations insist information cannot simply vanish. Gravity appears to suggest otherwise. The two greatest achievements of 20th century physics begin quietly disagreeing. Neither theory is obviously wrong. Neither willingly yields. For decades, this disagreement became one of science's deepest unsolved mysteries. Some researchers argued information truly escapes, hidden within unimaginably subtle patterns inside Hawking radiation. Others believed entirely new physics must emerge near the horizon. Still others proposed that our understanding of space itself remained incomplete. Notice how the mystery has evolved. We no longer ask only what lies inside a black hole. We now ask how reality remembers anything at all. Perhaps memory is more fundamental than matter. Perhaps information survives even when every visible object disappears. Perhaps existence itself resembles a story continually rewritten, rather than a collection of permanent things. The fireplace has almost gone dark. Only a few glowing embers remain. They appear small, fragile, yet each still carries warmth from flames that danced long ago. In much the same way, Hawking radiation may be carrying ancient messages across unimaginable ages. The light on it is almost impossibly faint, the code almost impossibly subtle. But if those messages truly exist, then somewhere within them may lie the complete history of everything a black hole has ever embraced. Have you ever misplaced an old photograph? At first, you search the obvious places, a familiar drawer, a bookshelf, between the pages of a favorite novel. You remember exactly what the photograph looked like, the faces, the season, the sunlight. You know it existed because you once held it in your hands. Yet as the search continues, a quiet unease begins to grow. Has it truly disappeared? Or has it simply moved somewhere beyond your memory? This feeling lies surprisingly close to one of modern physics' greatest puzzles. The universe itself may never lose anything, but proving that belief has become extraordinarily difficult. Every ordinary experience encourages the opposite conclusion. We spill coffee onto notebooks, old computers fail, voices fade from memory, buildings collapse, entire forests return to soil. Everywhere we look, order appears to dissolve into disorder. Physics agrees that order changes. It hesitates to say it vanishes. Imagine a 1,000-piece jigsaw puzzle spread across a table. Once completed, the image is perfectly clear. Now shake the box until every piece becomes mixed together. The picture seems lost, yet every piece still exists. Nothing has disappeared. The information needed to rebuild the image remains present. Although recovering it requires patience beyond imagination, nature often behaves this way. Complexity hides information, it rarely destroys it. This principle sits quietly beneath quantum mechanics. Every interaction, every collision, every exchanged particle follows mathematical rules that preserve information. The future evolves from the present without forgetting the past. If someone possessed complete knowledge of every particle in the universe, the equations suggest that, in principle, every previous arrangement could be reconstructed. Reality becomes unimaginably difficult to calculate, not impossible to remember. Then black holes enter the story. Suppose an astronaut carries a handwritten journal toward the event horizon. Inside are childhood memories, family names, favorite songs, sketches of distant mountains. The notebook crosses the horizon and disappears forever from outside view. Where is its information now if the black hole later evaporates into featureless Hawking radiation? Can those pages somehow be reconstructed? Or has the journal truly been erased from existence? This question became known as the black hole information paradox because it places two magnificent theories into quiet conflict. Einstein's gravity predicts one outcome. Quantum mechanics strongly favors another. Both have survived every experimental test available so far. Both describe nature with astonishing precision. Yet, together, they seem unwilling to tell the same story. For many years, physicists divided into different camps. Some believed information really is destroyed. Others insisted quantum mechanics must ultimately prevail. Still others suspected the disagreement existed only because humans were asking the wrong question. Science often progresses this way, rarely through immediate certainty, more often through patient disagreement. Imagine several people standing around an enormous sculpture hidden beneath a cloth. One feels only a smooth curve. Another touches a sharp edge. A third notices rough stone. Each description seems incomplete. None is necessarily wrong. Only when the covering finally lifts does the larger picture emerge. Perhaps black holes have always been inviting exactly this kind of patience. One proposed solution suggests that information escapes within Hawking radiation itself. At first glance, the radiation appears perfectly random, much like static heard between radio stations. Yet randomness can be deceptive. Think about a page filled with tiny dots, Viewed from across a room, it appears meaningless. Walk closer. Patterns emerge. Closer still. Letters become visible. Eventually, an entire sentence appears where only scattered points once existed. Some researchers believe Hawking radiation may behave similarly. The escaping particles seem random because the hidden pattern is unimaginably subtle. Tiny correlations between countless particles could preserve every detail swallowed by the black hole. Although decoding that message might require computational abilities beyond anything civilization could ever build, another idea feels even stranger. Perhaps information never truly crosses the horizon at all. Instead, it becomes spread across the boundary itself, almost like ripples remaining upon the surface of a pond after a stone sinks beneath. The stone disappears from sight. The ripples continue carrying news of its arrival. This image inspired remarkable new thinking about the nature of space. If the horizon records information, perhaps boundaries throughout the universe play a far greater role than anyone first imagined. The implications quietly expand beyond black holes. Could reality itself resemble an enormous archive? Could every interaction leave traces written into the geometry of space-time? Modern theoretical physics increasingly explores questions that once belonged almost entirely to philosophy. The separation between those disciplines grows softer every decade. Curiously, everyday life offers gentle reminders of this possibility. Walk through a forest after autumn rain. Leaves cover the ground. Someone passes ahead of you. Long before you arrive, you never meet them, yet bent grass, fresh footprints, broken twigs, a faint scent carried by cool air all reveal their presence. Absence still leaves evidence. Perhaps black holes work in much the same way. The traveler disappears. The record remains. Human memory behaves similarly. A loved one may leave this world. Their voice gradually fades. The exact sound of their footsteps becomes difficult to recall. Yet countless small traces continue shaping the lives of others. Habits survive. Stories survive. Kindness survives. Information transforms into influence. The universe may preserve history through equally subtle pathways, not by freezing moments forever, but by allowing every event to echo into what follows. This perspective changes the emotional meaning of the paradox. Instead of asking whether black holes erase existence, we begin asking how existence quietly rewrites itself. The distinction matters. Erasure suggests finality. Transformation suggests continuity. Nature repeatedly favors the second. Stars become heavier elements. Those elements become planets. Planets become oceans. Oceans become life. Life becomes memory. Memory becomes culture. Nothing remains unchanged. Yet every chapter grows from those before it. The information paradox may simply be another chapter waiting for its complete language. Many physicists now believe that information almost certainly survives. The challenge is no longer whether it exists, but where it hides and how it is encoded. The answer may require a future theory uniting gravity with quantum mechanics into one coherent description of reality. Such a theory has not yet arrived. The puzzle remains beautifully unfinished, and perhaps that incompleteness is itself valuable. Mysteries encourage careful observation. They remind us that certainty is not the only path toward understanding. Sometimes the deepest wisdom begins with admitting how much still waits beyond the edge of today's knowledge. Our search for the missing photograph has quietly become a search for something much larger, not merely lost information, but the architecture of reality itself. To continue that search, we must now consider a breathtaking possibility. What if the entire three-dimensional universe around us is only the visible expression of information written upon a distant cosmic surface? Stand beside a perfectly still lake just before sunrise. The water seems almost like polished glass. Mountains appear beneath your feet. Clouds float below the shoreline. Trees stretch downward into impossible depths. For a brief moment, it feels as though two complete worlds exist at once, one above, one below. Reach toward the reflection. However, and your hand touches only a thin surface. The depth was never truly there. your eyes quietly transformed 2 dimensions into the convincing illusion of 3. This familiar experience offers one of the gentlest entrances into an idea that once sounded almost impossible: the holographic principle. Its name carries the flavor of science fiction. Its origins come directly from mathematics. The journey begins with a question already waiting for us. Why does a black hole seem able to store information according to the area of its event horizon rather than the volume inside? Imagine building 2 libraries. The first occupies a modest house. The second fills an enormous cathedral. Common sense suggests the larger building stores more books because it possesses greater interior space. Black holes refuse to follow this intuition. Their information appears connected to surface area, not interior volume. That single observation quietly unsettled many physicists. If information depends upon boundaries, perhaps boundaries matter far more deeply than anyone imagined. Picture a wax seal pressed into warm clay. The seal itself has depth, raised patterns, tiny carved details, yet the clay receives only an imprint upon its surface. Remarkably, that flat impression preserves enough information to reproduce the original design. The 3-dimensional object leaves behind a 2-dimensional record. This simple image captures the heart of holographic thinking. Perhaps reality itself behaves similarly. Perhaps the full richness of 3-dimensional space emerges from information written upon a distant 2-dimensional boundary. Notice how extraordinary this sounds. You feel height, width, depth. You move through rooms, climb hills, reach toward stars. Everything in daily experience insists that 3 dimensions are unquestionably real. The holographic principle does not deny those experiences. Instead, it suggests they may emerge from something even more fundamental. A familiar comparison comes from cinema. When you watch a film, characters seem to inhabit landscapes stretching toward distant horizons. Mountains tower above valleys. Cities appear filled with depth. Yet, every image lives upon a flat screen. Careful arrangements of light persuade your brain to perceive dimensions that are not physically present. Nature may possess an elegance even more astonishing. The universe might generate genuine, 3-dimensional reality from information distributed across an unimaginably distant cosmic surface. This idea did not arise from imagination alone. It grew naturally from attempts to resolve the information paradox. During the 1990s, several theoretical physicists noticed remarkable mathematical relationships between gravity inside certain regions of space and quantum theories defined only upon their boundaries. The equations matched with astonishing precision. 2 completely different descriptions produced identical physical predictions. It was as though 2 maps, drawn in entirely different styles, somehow guided travelers through exactly the same landscape. Among the most influential contributors was Juan Maldacena, whose work revealed a powerful correspondence between gravity and quantum field theory. Although the original mathematics describes a highly specialized universe unlike our own in important ways, it provided something priceless, evidence that holographic descriptions might be far more than clever metaphors. The possibility remains under active investigation today. No one has proven that our universe is literally holographic. Yet many researchers believe the principle captures something profoundly true about gravity itself. Imagine reading a musical score. The notes printed across the page remain perfectly still. No sound exists within the ink. Yet when musicians perform the score, melodies emerge, harmony fills the room. Emotion appears from silent symbols arranged upon paper. Information becomes experience. Perhaps space-time behaves similarly. The fundamental description of reality could exist in one form. The living universe we inhabit becomes another, both equally real, both describing the same underlying truth. There is something quietly beautiful about this possibility. Human beings often assume complexity always requires more substance, larger buildings, more material, greater volume. Nature repeatedly teaches a different lesson. A tiny strand of DNA contains instructions for an entire organism. A single seed remembers the architecture of a towering tree. Small beginnings quietly unfold into astonishing richness. Why should the universe itself not follow the same pattern? The holographic principle also changes how we imagine distance. Suppose every event occurring throughout space contributes information to an invisible cosmic boundary. Every star, every planet, every photon, every heartbeat. Reality becomes less like scattered objects drifting through emptiness and more like one continuous tapestry woven from relationships, separate threads, one fabric. Ancient philosophers often searched for hidden unity beneath apparent diversity. Modern physics approaches a remarkably similar destination through mathematics rather than meditation. The language differs. The longing feels strangely familiar. Still, caution remains essential. Science advances by testing ideas against observation. The holographic principle has produced remarkable mathematical successes, especially within theoretical physics. Yet direct experimental confirmation remains elusive. Researchers continue searching for subtle clues that might reveal whether space-time truly emerges from deeper informational structures. The mystery remains open, and perhaps that openness is precisely what makes it so captivating. We stand in a rare moment where imagination and calculation walk side by side. Neither has reached the final destination. Both continue listening. If holographic ideas eventually prove correct, they may transform nearly every branch of fundamental physics. Gravity, quantum mechanics, cosmology. Even our understanding of what space actually is could require gentle revision. The reflection upon the quiet lake now seems a little different. It was never merely an illusion. It was a reminder. Sometimes surfaces hide astonishing depth. Sometimes depth itself emerges from surfaces. Reality may be far more subtle than either intuition alone or mathematics alone first suggests. Yet even holography does not answer every question. Somewhere beyond the event horizon, equations still point toward a place where space-time appears to fold into an impossible limit, a region where every known theory begins quietly losing its certainty. Physicists have given that mysterious destination a simple name: the singularity. Understanding why that word remains incomplete will carry us deeper than ever before into the hidden heart of the black hole. Take a sheet of paper into your hands. Hold it gently by the edges. At first, it appears perfectly flat. Draw two small dots near opposite corners. The distance between them seems fixed. If an ant began walking from one dot to the other, the journey would take time. Every bar step would matter. Every inch would remain exactly where it has always been. Now slowly fold the paper. The two dots drift closer. Fold it further. Eventually, they almost touch. Nothing happened to the ant's path across the surface. Yet, the geometry surrounding that path changed completely. This quiet image has helped generations of physicists describe one of the strangest features of space-time. Distance is not always absolute. Geometry matters, more deeply than intuition first suggests. Einstein taught us that gravity is geometry rather than an invisible force. Massive objects curve space-time. Planets follow those curves. Stars follow them. Even light quietly obeys them. The larger the mass, the deeper the curvature becomes. Black holes represent the most extreme curvature ever discovered. Every road through space-time bends inward. Every path gradually converges. Every familiar coordinate system begins losing its usefulness. Continue following the mathematics, and eventually, another remarkable prediction appears. The singularity. The word often creates dramatic images. An infinitely small point, infinite density, infinite gravity, a place where everything ends. These descriptions are useful only if we remember one important fact. Infinity inside physics usually signals that our equations have reached their limit, not necessarily that reality itself has. Imagine using an old paper map to navigate a modern city. Most streets appear correctly. Parks remain recognizable. Rivers occupy their expected places. Then you reach an entirely new neighborhood, built after the map was printed. The paper suddenly becomes silent. Blank space replaces living streets. The city did not disappear. The map simply stopped knowing what to draw. Many physicists believe singularities resemble those blank regions. General relativity guides us with astonishing precision almost everywhere. It predicts planetary motion, gravitational waves, black holes, the expansion of the universe. Yet, when space-time becomes compressed beyond a certain limit, the equations produce infinities. Those infinities are often interpreted not as physical objects, but as gentle warnings. Something important is missing. The missing piece almost certainly belongs to quantum gravity. Today, we possess two magnificent descriptions of nature. General relativity governs enormous scales. Quantum mechanics governs astonishingly tiny ones. Both succeed brilliantly within their own domains. Neither completely embraces the other. Inside a black hole, both become equally necessary. Gravity becomes overwhelming. Distances become unimaginably small. The two great theories finally meet and begin quietly disagreeing. Imagine trying to describe an ocean using only the language of individual water molecules. Every molecule behaves correctly, yet waves, tides, and currents emerge only when countless molecules act together. Reverse the problem. Describe the ocean only through waves while ignoring individual molecules. Again, something essential disappears. Reality often requires more than one perspective. Black holes may be telling us exactly that. Some researchers imagine that the singularity never truly forms. Quantum effects may become so powerful that space-time refuses to collapse into infinite density. Instead, an entirely new structure could emerge. Others propose that space acquires a smallest possible scale, much as matter consists of atoms rather than infinitely divisible substance. If space-time itself possesses fundamental building blocks, then endless compression simply cannot occur. Several modern approaches explore this possibility. Loop quantum gravity suggests that space may have an underlying discrete structure, woven from unimaginably tiny loops. String theory imagines the most fundamental ingredients not as points, but as vibrating one-dimensional strings existing within richer geometries than everyday experience reveals. These frameworks differ profoundly. Neither has yet received decisive experimental confirmation. Yet both share an important intuition. The singularity may not be nature's final answer. It may be the place where today's language quietly reaches its edge. There is something unexpectedly familiar about this. Human understanding has often mistaken the limits of knowledge for the limits of reality. Ancient maps ended with blank oceans. People once believed continents stopped there. Then ships continued sailing. The blankness belonged to the map, not the Earth. The same pattern has repeated throughout history. Invisible microbes explained disease. Atoms explained chemistry. Galaxies expanded the known universe. Each discovery revealed that apparent endings were often invitations to keep exploring. Perhaps singularities belong to that same tradition, not walls, thresholds. There is another subtle reason physicists remain cautious. Nature rarely tolerates true infinities. Measure temperature. It remains finite. Measure mass. Finite. Measure energy. Finite. Whenever equations suddenly predict infinity, experienced scientists often suspect that the mathematical framework has wandered beyond the region where it should be trusted. The equations are not failures. They are signposts. They quietly point toward deeper theories still waiting to be discovered. Imagine listening to an orchestra performing behind a closed curtain. You hear beautiful music, yet occasionally, one instrument produces notes unlike anything expected. Those unusual sounds do not prove the orchestra has collapsed into chaos. More likely, they suggest there are musicians you have not yet seen. Black holes may be playing exactly this role within physics. They expose hidden instruments, hidden structures, hidden principles. Every paradox they create becomes another clue. Perhaps the center of a black hole is not an infinitely dense point at all. Perhaps it is a bridge. Perhaps it is a quantum region, unlike anything ordinary space-time can contain. Perhaps entirely new geometry quietly replaces the classical picture before infinity ever arrives. For now, no experiment can settle the question. The singularity remains concealed behind the event horizon, safely hidden from direct observation. Nature keeps its deepest chamber closed, at least for the moment. Yet mathematics continues, knocking gently upon that door, and every decade, the echoes become a little clearer. If the singularity is not the end, another possibility naturally appears. Could space-time continue beyond it? Could collapse become connection? Could a black hole hide not merely an ending, but a passage leading somewhere else entirely? That question leads us toward one of the most enduring ideas ever imagined in modern physics, the possibility of a bridge through space-time itself. Walk through an ordinary doorway inside your home. You rarely pause to think about it. One moment you stand in the kitchen. A single step later, you enter another room. The doorway occupies only a small space, yet it quietly connects two places that would otherwise remain separated by walls. Every building depends upon such simple passages. They shorten journeys. They reshape movement. They make large structures feel whole. Now imagine a doorway that connects not two rooms, but two distant regions of the universe. This idea has fascinated both physicists and storytellers for generations. Its scientific name is surprisingly modest, an Einstein-Rosen bridge. Most people know it by another name, a wormhole. The image becomes easier to understand if we return to our folded sheet of paper. Earlier, two distant dots moved together simply because the paper itself changed shape. The traveler walking across the surface still faced a long journey. Yet, someone able to move through the folded geometry could step directly between the 2 points. The shortcut did not ignore distance. It changed geometry. This simple distinction matters enormously. Science fiction often portrays wormholes as glowing tunnels surrounded by swirling light. Reality, if such structures truly exist, would almost certainly appear far stranger and far quieter. According to Einstein's equations, space-time itself can possess solutions resembling bridges. These mathematical passages connect different regions without requiring anything to travel faster than light through ordinary space. The equations allow them. Nature has not yet confirmed them. This difference deserves patience. Mathematics frequently reveals possibilities long before observation determines which possibilities reality actually chooses. Black holes entered physics through equations decades before telescopes confirmed their existence. Gravitational waves were predicted a century before detectors finally heard them. Sometimes the universe rewards mathematical imagination. Sometimes it gently declines. Wormholes remain suspended between those two outcomes. The original Einstein-Rosen bridge emerged naturally from solutions describing black holes. At first glance, it seemed wonderfully promising. Perhaps matter falling into one black hole could emerge elsewhere through an unseen passage. Further analysis introduced a quiet disappointment. The bridge collapses too quickly. Anything attempting to cross would find the passage closing almost instantly. Imagine building a tunnel through soft sand. Before the first traveler reaches the middle, the walls begin collapsing inward. The entrance existed. The journey did not. For many years, this seemed to settle the matter. Wormholes became elegant mathematics rather than practical pathways. Then another question appeared. Could something hold the tunnel open? Engineers reinforce bridges with steel because gravity pulls them downward. Perhaps space-time also requires support. Physicists discovered that maintaining a traversable wormhole would demand an unusual form of matter possessing what is often called negative energy density. The phrase sounds mysterious. Its meaning is subtle. Ordinary matter attracts through gravity. Negative energy would behave differently under certain conditions, resisting collapse in ways unfamiliar to everyday experience. Tiny quantum effects resembling negative energy do appear in laboratory phenomena, such as the Casimir effect. Two extremely close metal plates alter the quantum vacuum between them, producing measurable consequences. Yet, these effects are extraordinarily small. Nothing remotely approaching the amount required for a stable wormhole has ever been observed. So the dream remains mathematical, not impossible, not established, quietly waiting. There is another reason wormholes continue captivating scientists. They reveal unexpected connections between gravity and quantum mechanics. In recent years, Several theoretical studies have suggested that certain forms of quantum entanglement may possess deep relationships with Einstein-Rosen bridges. The playful phrase ER equals EPR summarizes this possibility, linking the initials of Einstein-Rosen bridges with the famous Einstein-Podolsky-Rosen description of quantum entanglement. The idea remains highly theoretical, yet it hints that space-time itself may emerge from patterns of quantum connection. Imagine a vast tapestry. Individual threads appear separate. Pull back. Hidden knots reveal that distant regions have always been connected beneath the visible pattern. Reality may contain similar hidden relationships. Entanglement already teaches us that quantum particles can share astonishing correlations across great distances. These correlations cannot transmit ordinary information faster than light. Yet they remind us that separation sometimes means less than intuition expects. Perhaps geometry and connection are more closely related than anyone first imagined. This possibility carries a quiet philosophical beauty. Human lives also appear separated by distance. Cities divide us, years divide us, generations divide us, yet memories, language, music, and kindness often bridge those gaps in ways difficult to measure. Connection sometimes survives where proximity does not. Nature repeatedly favors hidden relationship. Still, caution must remain our companion. No telescope has discovered a traversable wormhole. No spacecraft has entered one. No astronomical observation requires their existence. Every discussion rests upon theoretical exploration rather than direct evidence. Science grows strongest when imagination walks beside restraint. The temptation to transform possibility into certainty has misled many generations. Black holes have already taught us patience. Wormholes ask for the same. Suppose? However, that some form of stable bridge could exist somewhere within the cosmos. What might lie beyond another region of our own universe? A distant galaxy, unreachable by ordinary travel. Another epoch of cosmic history, or something even more extraordinary. Some cosmologists have dared to imagine that black holes might not merely connect distant places. They might connect entirely different universes, not neighboring galaxies, not remote clusters. Entire new realities born from gravitational collapse itself. The proposal remains speculative, yet it emerges naturally enough from several modern ideas that physicists continue examining it with genuine interest. The doorway we first imagined inside an ordinary house has quietly expanded beyond recognition. It no longer joins two rooms. It may join two cosmoses. Whether nature truly builds such passages remains unknown. But every worthwhile journey through science eventually reaches a place where evidence grows thin and careful imagination begins. We have arrived at one of those places. Beyond the bridge waits perhaps the boldest question of all. Could every black hole become the cradle of a newborn universe? Forever hidden from the one that created it, plant a single seed in quiet soil. Cover it gently, water it, then wait. For many days, nothing appears to happen. The ground remains unchanged. The garden seems empty, yet beneath the surface, an invisible transformation has already begun. Tiny roots search through darkness. Cells divide without sound. A new life slowly prepares itself long before anyone can see the first green leaf. Nature often hides beginnings inside places that appear to contain only endings. A fallen forest becomes fertile soil. The final breath of an ancient star creates the heavy elements that later become planets. Oceans and living creatures, death and birth frequently stand closer together than they first appear. This familiar rhythm offers a surprisingly gentle path toward one of cosmology's most daring ideas. What if the collapse that creates a black hole also gives birth to an entirely new universe? At first, the suggestion sounds almost mythical, yet it emerged not from poetry, but from careful attempts to understand gravity at its most extreme. According to Einstein's equations, a sufficiently massive star eventually exhausts the nuclear fuel supporting it against gravity. The outward pressure fades. The inward pull remains. Collapse begins. If enough mass is present, No known force stops the process before a black hole forms. From the outside, observers witness the birth of a new event horizon. The star disappears. Darkness remains. The story appears finished. But that conclusion belongs only to observers remaining outside. The mathematics inside the horizon becomes far more mysterious. As we explored earlier, classical relativity predicts a singularity. Many physicists suspect that prediction signals the limits of current theory rather than the final architecture of nature. If quantum gravity prevents true infinities, collapse may continue in ways today's equations only hint at. Imagine squeezing a spring. Push gently, it compresses. Push harder, it stores more energy. Eventually, you expect it to reach a limit. Now imagine a spring that, instead of breaking, quietly unfolds into an entirely new room hidden beyond the wall. The pressure does not simply disappear. It transforms into new space. Some cosmological models imagine black holes behaving in a similarly unexpected way. Rather than ending space-time, collapse could trigger expansion somewhere beyond ordinary observation. From our perspective, matter falls inward forever. From another perspective, an expanding universe begins. This remarkable possibility gained attention through several different theoretical approaches over the years. Physicists such as Lee Smolin explored variations of the idea while considering how universes might reproduce through black holes. Other researchers examined whether quantum gravity could replace singularities with expanding regions resembling new cosmic beginnings. The details differ. The shared intuition remains striking. Perhaps black holes are not merely graves for stars. Perhaps they are cosmic wombs. Imagine watching a raindrop strike the surface of a pond. From above, you see only a brief splash, followed by widening ripples. Now imagine microscopic creatures living within one tiny droplet, thrown upward by that splash. To them, their droplet contains an entire expanding world. They never observe the pond that produced it. Their universe begins with rapid expansion. The larger reality remains forever beyond direct observation. The comparison is imperfect. Every metaphor eventually reaches its limits, yet it captures the emotional scale of the idea. Our own universe began with extraordinary expansion. Space itself stretched rapidly. Galaxies eventually formed. Stars ignited. Planets emerged. Life appeared. If another universe experienced similar beginnings inside a black hole, its inhabitants might never know they originated from the collapse of a distant star within a parent cosmos. Their Big Bang would simply be the beginning. The parent universe would remain forever hidden behind its own horizon. There is an elegant symmetry here. To outside observers, black holes appear as regions from which nothing escapes. To hypothetical observers, inside a newborn universe, everything begins by expanding outward. The same geometry tells two entirely different stories depending upon perspective. Nature has offered us this lesson before. Observers moving differently measure time differently. Observers standing in different gravitational fields experience different rhythms. Perhaps observers separated by cosmic horizons also inherit different beginnings. Of course, honesty requires an important reminder. No evidence currently demonstrates that our universe was born inside a black hole. The proposal remains speculative. It belongs to the frontier, where mathematics continues exploring possibilities beyond present observation. Science neither accepts nor rejects such ideas simply because they sound beautiful. Beauty inspires questions. Evidence decides answers. Still, speculation grounded in physics possesses genuine value. It encourages researchers to search for predictions. Can such models explain features of our universe? Can they produce observable consequences? Can future measurements distinguish them from competing theories without testable questions? Imagination remains philosophy. With them, imagination becomes science. There is also a deeply human resonance hidden within this possibility. We often imagine endings as irreversible. The last page, the final goodbye, the extinguished flame. Yet the natural world repeatedly teaches another pattern. Leaves become soil. Soil nourishes roots. Roots lift forests toward sunlight. Every conclusion quietly feeds another beginning. Stars follow the same rhythm. Their deaths enrich galaxies. Galaxies create new stars. The universe appears less like a straight line and more like an endless cycle of transformation. If black holes also participate in that rhythm, they become symbols not only of disappearance, but of hidden renewal. The darkness surrounding them no longer represents simple absence. It becomes fertile silence, a place where possibilities gather beyond observation. Perhaps every collapsing star whispers the first chapter of a story no observer in our universe will ever read. Perhaps entirely new histories begin there. New galaxies, new skies, new beings wondering exactly the same questions we ask tonight. And if universes can indeed emerge from black holes, another astonishing thought naturally follows. Could countless universes already exist? Each born from another, each carrying slightly different laws, each quietly contributing to an endless cosmic family stretching far beyond anything our telescopes will ever reveal. Stand in a quiet canyon and speak a single word. Your voice leaves your mouth only once. Yet a moment later it returns. Then again, softer each time. The echo is never identical to the original sound. Rocks reshape it. Distance stretches it. Time gently weakens it. Even so, every echo carries unmistakable news that something once spoke into the silence. The universe may be filled with echoes we have not yet learned to recognize. Not echoes of voices, echoes of creation itself. If black holes can give birth to new universes, as some speculative theories suggest, then perhaps our own cosmos is only one member of a much larger family. A family so vast that words like countless and infinite begin losing their ordinary meaning. The idea of multiple universes did not begin with black holes. Several branches of modern physics reach similar possibilities through entirely different paths. Cosmic inflation, quantum mechanics, string theory. Each approaches the question from its own direction. Surprisingly, they sometimes arrive at landscapes filled with many possible universes rather than only one. This does not prove such universes exist. It reminds us that different mathematical roads occasionally point toward the same distant horizon. Imagine a forest stretching beyond every hill you can see, standing among the trees. You naturally believe your surroundings represent the whole forest. Climb high enough, however, and separate valleys slowly appear. Beyond them, more forests, then rivers, then mountains hiding still more forests beyond sight. Your first view was not wrong. It was incomplete. Human understanding of the cosmos may occupy a similar stage. For thousands of years, Earth seemed central. Later, the sun became central. Then even the sun became only one ordinary star among hundreds of billions inside a single galaxy. Soon afterward, our galaxy itself became one island among hundreds of billions more. History quietly encourages humility. Each time we believed we had reached the full picture, the horizon gently expanded. The multiverse continues that pattern. Perhaps our observable universe is not the whole of reality, only the region our light has reached since the beginning of cosmic expansion. Beyond that limit may lie more space forever inaccessible, because expansion carries it away faster than light can bridge the distance. Those distant regions would never communicate with us, yet they might still exist. Black hole cosmology introduces another possibility. Instead of neighboring regions within one immense cosmos, entirely separate universes could emerge through gravitational collapse. Every sufficiently massive black hole becomes the beginning of another expanding space-time hidden beyond its horizon. Imagine a vast family tree. Every branch grows from an earlier one. Each produces new branches of its own. No branch ever sees the entire tree. It knows only the path leading through itself. Lee Smolin developed a fascinating variation known as cosmological natural selection. The proposal remains speculative, yet elegantly simple. Universes capable of producing many black holes would also produce many offspring universes. over unimaginable generations. The laws of physics might gradually favor conditions encouraging black hole formation. Stars become the engines of cosmic reproduction. Galaxies become nurseries. Black holes become seeds. The idea borrows inspiration from biological evolution while remaining firmly within theoretical cosmology. Whether nature actually behaves this way remains unknown. Still, the comparison offers an unexpectedly peaceful perspective. Life evolves through countless generations. Perhaps universes do something similar. If so, the physical constants we measure today may not be arbitrary. They could represent one successful combination inherited through an immense lineage extending beyond anything we can observe. There is another profound implication. Many people ask why the laws of physics possess values allowing stars, planets, chemistry, and life change certain constants only slightly, and familiar structures may never form. Some researchers see this apparent balance as remarkable coincidence. Others invoke the anthropic principle, noting that observers naturally find themselves only in universes capable of producing observers. A multiverse offers another possibility. If countless universes exist with different properties, then at least a few would inevitably possess conditions suitable for complexity. We awaken inside one of those, not because it was chosen, because only such universes can ask the question. Again, honesty remains essential. None of these ideas has been directly observed. No telescope has photographed another universe. No instrument has detected a newborn cosmos emerging from a black hole. These proposals remain thoughtful attempts to extend known physics into regions where evidence remains incomplete. Science lives comfortably with such uncertainty. It has learned that patient questions often outlast confident answers. Yet something emotionally meaningful emerges even before certainty arrives. The universe may be far richer than immediate observation suggests. Reality may contain layers hidden not by magic, but by distance, geometry, and the finite speed of light. Our ancestors crossed oceans, believing nothing lay beyond the horizon. They found continents. Future generations may cross intellectual horizons with equal surprise. Perhaps the greatest discoveries awaiting humanity are not larger telescopes or faster spacecraft. Perhaps they are deeper ways of thinking, a new equation, a hidden symmetry, a quiet insight connecting ideas that once seemed unrelated. Every major scientific revolution has begun that way, with someone noticing a pattern almost everyone else overlooked. The canyon around us has now grown silent again. The original voice has long faded. Only memory remains. Perhaps the cosmos behaves similarly. Every black hole, every expanding universe, every galaxy, every civilization, each becomes an echo within a far larger composition. No single echo contains the whole song. Together, they may, whether or not the multiverse exists. Black holes have already transformed our understanding of reality. They have shown us that space bends, time stretches, information resists destruction. Horizons conceal rather than merely divide. And yet one question still remains. How can we ever test ideas hidden behind horizons we cannot cross? The answer may arrive not from entering black holes, but from listening with extraordinary patience to the faint whispers they leave behind. Walk across fresh snow just after sunrise. The world feels untouched. Every surface appears smooth and quiet. Then you notice a single line of footprints crossing the white field. The traveler has already disappeared beyond the trees. You never saw them arrive. You never heard their footsteps. Yet the snow remembers. Every print preserves a small piece of their journey. Nature often records events without keeping the traveler. This gentle observation leads us toward one of astronomy's newest ways of listening to the universe, not through light, through gravity itself. For most of human history, every astronomical discovery arrived through some form of light. Visible starlight, radio waves, X-rays, infrared warmth. Different colors revealed different stories, yet all belonged to the same family. They were messengers traveling across space. Gravity offers another language. Imagine holding one end of a long rope while a friend gently shakes the other. A wave travels toward you. The rope itself remains in place. Only the pattern moves. Space-time behaves in a remarkably similar way. When enormous masses accelerate, they create ripples that spread outward at the speed of light. These ripples are called gravitational waves. Einstein predicted them in 1916. For almost 100 years, they remained invisible to experiment. The waves reaching Earth are astonishingly small. A powerful gravitational wave changes the length of a 4-kilometer detector by less than the width of a proton. Measuring such a tiny distortion once seemed almost impossible, yet patience has always been one of science's greatest strengths. In 2015, instruments known as LIGO finally detected the first gravitational waves directly. 2 black holes had collided more than 1 billion light-years away. Their dance ended in a single violent merger. Part of their combined mass transformed directly into gravitational energy. Not light, not heat, ripples in space-time itself. By the time those waves reached Earth, they had become unimaginably faint. Even so, exquisitely sensitive lasers recorded their passing. For the first time in history, humanity had heard the universe through gravity. The discovery changed astronomy forever. Imagine spending your entire life watching silent films. Every story unfolds without sound. Then, one evening, someone quietly turns on the speakers. The same world suddenly becomes richer. New details appear. Hidden emotions emerge. Familiar scenes gain unexpected depth. Gravitational wave astronomy feels much the same. Black holes often hide from ordinary telescopes because they emit little or no light. Yet, when they merge, gravity itself announces the event across the cosmos. The universe whispers, "We have finally learned to listen." This achievement also offers hope for answering deeper questions. If black holes possess hidden structures beyond classical theory, perhaps future gravitational wave observations will reveal subtle deviations from Einstein's predictions. Tiny echoes following the main signal, slight changes in vibration, unexpected patterns within the fading waves. Physicists sometimes refer to these possibilities as gravitational echoes. The phrase should be understood carefully. No confirmed echoes have yet been observed. Several studies have searched. Some intriguing hints have appeared. None has reached convincing scientific agreement. Still, the search continues. Imagine standing inside an immense cathedral. Clap your hands once. The first sound arrives immediately. Then, softer reflections return from distant walls. Careful listeners learn about the building's architecture simply by studying those echoes. Perhaps black holes behave similarly. If quantum structures exist near the event horizon, the gravitational waves produced during mergers might reflect in subtle ways before fading into silence. The echoes would not show us another universe directly. They would reveal that space-time itself possesses richer architecture than classical relativity alone predicts. Sometimes absence becomes evidence. A detective reconstructs unseen events from scattered clues. An archaeologist rebuilds forgotten civilizations from broken pottery. Astronomers infer invisible planets by watching stars gently wobble. Science rarely begins with certainty. It begins with patterns. The coming decades promise extraordinary new observatories. Space-based detectors such as the planned Laser Interferometer Space Antenna, often called EIEC, aim to measure gravitational waves impossible to detect from Earth's noisy surface, free from earthquakes, traffic, and atmospheric disturbances. Instruments drifting through space may hear slower and deeper cosmic rhythms. They could observe supermassive black holes merging across billions of years. They might trace the growth of galaxies. Perhaps they will uncover surprises nobody currently expects. History suggests they probably will. Every new way of observing the universe has transformed our understanding. The telescope revealed moons around Jupiter. The spectroscope revealed the chemistry of stars. Radio astronomy uncovered pulsars. X-ray observatories exposed neutron stars and accreting black holes. Gravitational waves have only just begun telling their story. There is something quietly moving about this progression. Human beings evolved to hear birdsong, to notice rustling leaves, to recognize approaching footsteps. Now those same curious minds have built instruments capable of sensing distortions in space-time, created billions of years before Earth itself existed. Our senses remain humble. Our questions have grown magnificent. Yet humility remains essential. Many mysteries surrounding black holes still resist observation. Quantum gravity remains incomplete. The information paradox remains unresolved. The true nature of singularities remains hidden. Every answer we obtain gently reveals another horizon waiting beyond. Perhaps that endless unfolding is not a weakness of science. Perhaps it is its greatest strength. Knowledge does not conclude with certainty. It deepens through curiosity. The footprints across the snow eventually disappear beneath fresh weather. The traveler continues elsewhere. The record slowly fades. Gravitational waves behave similarly. They pass through galaxies, across empty space, through our own planet, then onward into darkness, leaving only brief traces inside delicate instruments built by patient hands. From those tiny traces, humanity slowly reconstructs stories older than civilization itself. Soon we will reach the final question, not what black holes hide, not whether universes bloom within them, but what all these possibilities quietly reveal about us, about consciousness, about wonder, about our brief place beneath the oldest sky we have ever known. Imagine standing beside a lonely lighthouse just before dawn. The sea is calm. The horizon seems endless. Every few seconds, the great beam of light slowly sweeps across the water before disappearing once more into darkness. Somewhere beyond that horizon may be distant ships, hidden islands, entire coastlines you cannot yet see. The absence of evidence does not mean the ocean ends there. It simply marks the farthest distance your eyes can presently reach. Science has always lived beside that horizon. Every generation inherits a boundary between what is known and what still waits beyond observation. Sometimes that boundary retreats quickly. Sometimes it remains stubbornly fixed for centuries. Black holes now occupy one of those remarkable frontiers where knowledge and mystery quietly share the same shoreline. Modern astronomy has revealed astonishing facts with extraordinary confidence. We know black holes exist. We know stars collapse under gravity. We know event horizons prevent light from escaping. We have photographed the glowing shadow surrounding supermassive black holes. We have measured gravitational waves from black hole mergers. These achievements are no longer speculation. They belong to observation. Beyond them lies another landscape. What happens inside the event horizon? Does information truly survive? Does Hawking radiation preserve hidden patterns? Does quantum gravity eliminate singularities? Could black holes seed entirely new universes? Could space-time itself emerge from information? These questions remain beautifully unfinished. Sometimes people feel disappointed by uncertainty. Science rarely does. Uncertainty is not failure. It is direction. Imagine assembling an enormous jigsaw puzzle across a wooden table. Thousands of pieces already fit together. Rivers connect naturally with forests. Mountains meet clouds. The image grows clearer every hour. Yet one region near the center remains incomplete. Empty spaces separate several clusters that obviously belong together. No thoughtful observer would throw away the completed sections simply because the final pieces remain missing. Instead, the missing pieces become the most valuable part of the puzzle. They tell you exactly where to continue searching. Black holes perform this role within modern physics. General relativity describes gravity with breathtaking precision. Quantum mechanics predicts microscopic behavior with equal success. Each theory has transformed civilization. Neither comfortably explains the deepest interior of a black hole. Nature quietly invites us to continue. There is another lesson hidden here. Human history repeatedly demonstrates that certainty often arrives too early. Ancient astronomers believed Earth rested motionless at creation's center. Later generations believed the Milky Way contained the entire universe. Each conclusion felt complete until new evidence gently expanded reality once again. Perhaps our present understanding will someday appear equally incomplete. That possibility should not discourage us. It should inspire gratitude. We are fortunate to live during an era when so much remains discoverable. Children looking through telescopes today may help answer questions that have quietly accompanied humanity for generations. Some future physicist may discover the mathematical bridge joining gravity and quantum mechanics. Some future observatory may detect subtle signatures hidden within Hawking radiation. Some future experiment may reveal that space-time possesses an architecture nobody currently imagines. Every scientific revolution begins as tomorrow's possibility. The universe has always rewarded patient curiosity. It has never rewarded haste. There is something deeply calming about this rhythm. We often feel pressure to solve every mystery immediately, to reach conclusions quickly, to remove uncertainty from our lives. The cosmos follows another pace. Stars require millions of years to mature. Galaxies evolve across billions. Black holes slowly evaporate over spans so vast that language struggles to contain them. Against such backgrounds, human impatience quietly softens. We remember that understanding itself is a journey rather than a destination. Perhaps this explains why astronomy so often brings unexpected peace. Looking outward gently rearranges the scale of our worries. The difficult conversation from yesterday, the unfinished task waiting tomorrow, the anxious thought returning each evening, none becomes meaningless. They simply find their proper place within a much larger story. Black holes teach humility, not because they frighten us. They remind us that reality remains wonderfully richer than our present understanding. Even after centuries of observation, the universe still reserves entire chapters beyond the reach of certainty. That reserve is not emptiness. It is invitation. Imagine once more the lighthouse. Its beam never illuminates the entire ocean at once. Only one narrow path through darkness. Yet sailors navigate successfully because the light continues returning. Science works in the same quiet way. Each discovery illuminates only a small region. Another sweep reveals another, generation after generation. The beam slowly travels farther. No single lifetime completes the voyage. Every lifetime extends it. Perhaps that is enough. Perhaps wisdom does not require standing at the end of knowledge. Perhaps wisdom means walking peacefully toward horizons that always remain slightly ahead. The questions surrounding black holes remind us of something profoundly human. We are creatures who ask. Long before telescopes, long before mathematics, people looked upward and wondered. The tools have changed. The wondering has not. Soon our journey will come gently back to Earth. We began with a falling coin, an ordinary object obeying familiar gravity. From that simple moment, we traveled across collapsing stars, curved space-time, quantum mysteries, information paradoxes, newborn universes, and gravitational echoes. Now only one quiet reflection remains. What all these extraordinary ideas ultimately reveal about our own place within the silent universe. Tonight began with something almost too ordinary to notice. A small coin slipping from your fingers, a familiar pull toward the floor. A moment repeated countless times throughout every human life. From that simple beginning, we quietly followed gravity far beyond the world where our instincts evolved. We crossed the silent boundaries of collapsing stars. We watched light surrender to curved space-time. We listened to time itself slow beneath overwhelming gravity. We stood beside horizons from which no signal returns. We imagined libraries written upon the surface of darkness. We considered universes hidden beyond impossible depths. And now, after such an immense journey, we arrive back where every meaningful journey eventually ends, home. Not because we have solved every mystery, because we have learned how to look differently. The night sky above your home appears unchanged. The same stars remain scattered across the darkness. The moon continues its patient orbit. Distant galaxies still drift almost beyond imagination, yet perhaps they no longer feel quite as distant. Every atom inside your body once belonged to an ancient star. Long before Earth existed, enormous furnaces forged the carbon in your cells, the oxygen in your lungs, the calcium in your bones, and the iron flowing quietly through your blood. Those stars exhausted themselves. They collapsed. They exploded. Their remains drifted through silent space until gravity gathered them once more into new worlds. Your existence already carries the memory of stellar endings becoming unexpected beginnings. Black holes simply extend that ancient rhythm into deeper mystery. Perhaps nothing illustrates the character of science more beautifully than this. Every answer worthy of celebration quietly creates another question worthy of pursuit. Humanity photographed a black hole for the first time, and instead of closing the story, the image opened entirely new chapters. Every observation sharpened the paradox. Every calculation revealed richer complexity. Every discovery widened the horizon. Knowledge behaves much like walking toward the sea. The farther you travel, the broader the shoreline becomes. Some people find this unsettling. Others discover peace within it. There is something strangely comforting about living inside a universe that cannot be exhausted by curiosity. Imagine a child standing beside the ocean for the very first time. They do not measure the water's depth. They do not calculate the tides. They simply watch the waves arrive one after another with quiet wonder. That sense of wonder is not replaced by science. It matures through science. Understanding how tides form never diminishes the beauty of the sea. Learning how stars shine never weakens the night sky. Knowing how black holes curve space-time does not reduce their mystery. It refines it. The greatest discoveries rarely remove wonder. They teach wonder where to look next. Black holes have done exactly that. Once they were imagined as simple cosmic traps. Then they became laboratories for Einstein's gravity. Later, they challenged quantum mechanics. Today, they stand at the meeting point of nearly every profound question in modern physics. Time, space, information, entropy, reality. Consciousness has not yet entered those equations. Yet every question about the universe ultimately passes through conscious minds willing to ask. Perhaps that is one of the quietest miracles of all. The cosmos became capable of wondering about itself, not through magic, not through destiny, through countless generations of stars creating atoms, planets creating oceans, oceans nurturing life, and life gradually learning to observe the sky above it. The chain feels impossibly long, yet every link belongs to the same unfolding story. Somewhere tonight, another child is looking upward for the first time. Some future physicist is still asleep. Some future telescope has not yet been built. Some future equation exists only as a possibility waiting inside an ordinary human mind. History reminds us never to underestimate such beginnings. Newton once watched an apple fall. Einstein quietly imagined riding beside a beam of light. Hawking asked what quantum physics might whisper beside an event horizon. Each journey began with a simple question, not certainty, curiosity. Perhaps your own quiet moments of curiosity belong to that same tradition. Not because everyone becomes a scientist, because every thoughtful question enlarges the world a little, even when no immediate answer appears. Outside, the night continues. The earth turns gently beneath your feet without asking for attention. The moon silently guides distant tides. The sun, though hidden now, continues fusing hydrogen into light that will arrive tomorrow morning with perfect patience, far beyond those familiar rhythms. Black holes continue their own silent work. Some consume wandering stars. Some anchor the centers of galaxies. Some may slowly radiate away across spans of time so immense that today's universe will one day feel unimaginably young by comparison. Whether they hide new universes, whether information survives exactly as quantum theory predicts, whether space-time ultimately emerges from deeper patterns, these questions remain open. That openness is not a weakness. It is an invitation to future generations, an invitation to careful observation, an invitation to humility, above all, an invitation never to mistake today's horizon for the edge of reality itself. As this night slowly draws toward its quiet conclusion, allow the questions to remain gentle companions rather than unfinished burdens. They do not demand immediate answers, like distant stars. They can simply remain present, calm, silent, patient, Perhaps the greatest secret hidden inside a black hole is not another universe. Perhaps it is a reminder. Reality has always been deeper than first appearances. The familiar floor beneath your feet rests upon a planet circling an ordinary star. That star drifts within one galaxy among hundreds of billions. Those galaxies continue moving through an expanding cosmos whose ultimate structure we are only beginning to understand. And somewhere, beyond every horizon we have explored tonight, the universe continues unfolding without hurry, whether anyone is watching or not.